Welcome back to the Deep Dive. As your guides, we're diving into the latest and most impactful AI and ML research. We always focus squarely on the technical intricacies and the transformative implications of the technologies we unpack. And just a reminder, to stay on top of the cutting edge in AI and ML, make sure to visit our webpage, neuralintel.org, and you can also subscribe to us on YouTube. Okay, so let's unpack today's topic. Imagine this.
Yeah.
Being able to instantly capture and really understand the detailed 3D geometry of a moving scene. We're not just talking about a static room, right? Think more like a bustling street, cars, pedestrians, maybe a vast dynamic environment like a factory floor, and doing it all in real time, continuously.
Right, capturing truly dynamic scenes, complex structures on the fly. That's the goal.
Exactly. And today we're taking a deep dive into a really fascinating new approach that promises to make this a reality. And it draws inspiration from, well, a pretty unexpected place, the world of large language models.
It's a fascinating connection.
Our mission in this deep dive is to explore STREAM3R, Scalable Sequential 3D Reconstruction with Causal Transformer. This paper, it presents a novel framework for 3D reconstruction, but specifically from streaming images, and it directly addresses some major kind of long-standing limitations of the existing methods.
Yeah, limitations that have really held back progress in certain areas.
We'll unpack the core technical challenges, the things that have plagued this field. We'll look at STREAM3R's elegant solution, which is surprisingly intuitive in some ways. We'll cover its impressive performance benchmarks that really set it apart. And of course, the profound technical implications for applications across AI and robotics.
There are definitely some aha moments in how they approach this.
Get ready for some truly illuminating insights into how they cracked this complex problem. So let's start right at the beginning. Why is reconstructing detailed 3D geometry from images such a, well, the paper calls it a crux in computer vision? Why is this so fundamental? And honestly, why has it been such a persistent hurdle?
It's fundamental because, well, 3D geometry is basically the bedrock for so many advanced applications. Anything that aims to intelligently interact with our physical world needs it. Think about an autonomous vehicle. It needs to understand not just what objects are around it, like cars or people.
Right, object detection.
Exactly. But also their precise distance, their shape, even maybe their velocity to navigate safely, anticipate movements, make those split-second decisions.
Yeah.
Or for virtual reality, augmented reality. Creating truly immersive experiences means accurately mapping the real world into a digital space, or seamlessly blending digital objects into your real-world view with perfect alignment. If that 3D understanding is off, even by a few centimeters,
the illusion just shatters. It feels wrong.
it breaks completely. It becomes jarring. And then in robotics, a robot needs to perceive its environment in 3D to, say, manipulate objects, avoid obstacles, plan its movements, especially in complex, unstructured places. Without precise and crucially continuously updated 3D geometry, these systems are essentially operating blind, or maybe with very limited static awareness.
So it's really the foundational layer, the thing that lets intelligent systems actually interact with our dynamic physical world.
It absolutely is. It's the difference between a robot just, existing in a space and truly understanding it.
That makes a lot of sense. So if understanding 3D geometry is truly the bedrock, why aren't we seeing systems flawlessly navigating dynamic environments right now? What have been the historical approaches, and where do they fall short when you need speed and continuous understanding?
Well, historically, a very common approach involved methods like structure from motion, or SFM, and multi-view stereo, MVS.
Right, SFM and MVS. Heard of those?
Yeah, they're often described as these traditional visual geometry methods. They tackle the problem by solving a whole series of sub-problems, often using handcrafted designs and pipelines. So essentially, they take a collection of images, maybe photos you took walking around a building, find common features across them, and then use pretty complex geometric computations optimization techniques to figure out where the cameras were for each photo.
The camera poses.
Exactly, the poses. And then what the 3D structure of the scene actually looks like. The main issue here, though, is their batch processing nature. They're designed to work on a fixed set of images, all available at once, which you can then process offline.
Okay, so not for live video feeds.
Not at all. That makes them entirely unsuitable for continuous streaming input. Like, imagine a camera on a drone flying through a forest, or a robot navigating a warehouse in real time. If you tried to use them in a streaming scenario, you'd feed them each new image, and they'd effectively have to resolve the entire problem from scratch every single time a new image comes in, completely disregarding all the prior computation.
Wow, okay. That sounds incredibly inefficient.
It's computationally brutal. and completely impractical for real-time applications. It's like trying to watch a movie by, I don't know, rebuilding the entire film reel from individual frames for every single frame you want to see.
Right. Great analogy. So fantastic for static stuff like building a 3D model of a museum from old photos.
Perfect for that.
But useless for a self-driving car that needs to know what's happening right now.
Precisely.
Okay, but what about the newer methods? Things that have really pushed visual realism, like neural radiance fields, NeRF, or Gaussian splatting. They create these incredibly realistic 3D views, right?
They absolutely do. NeRF and Gaussian splatting they've revolutionized what the paper calls high-fidelity novel view synthesis using continuous volumetric representations. They can generate stunningly realistic new views of a scene from basically any angle, often achieving photorealistic quality. It's quite amazing visually.
But there's a catch, I assume.
There's a crucial limitation. They are typically trained per scene with no learned priors. The paper calls this the tabula rasa assumption.
Tabula rasa, blank slate.
Exactly, blank slate. So if we connect this back to the bigger picture, these methods, yeah, they produce stunning visuals, but they're kind of like rebuilding a complex Lego model from scratch every single time you want to add a new piece or just look at it differently. They lack that inherent understanding of common shapes, textures, structures that a data-driven model could learn from, vast amounts of experience.
Okay, so they don't generalize well.
Not in that sense. It means they require extensive data, lots of views for each specific scene you want to reconstruct. And they converge very slowly. Often takes hours, sometimes even days to train for just one scene. And because they start from that blank slate every time, they have poor generalization to sparse or occluded inputs. They're not designed to fill in gaps intelligently or make educated guesses about unseen parts based on prior experience with similar scenes.
So they can't really infer what's behind a pillar, for instance, because they haven't learned general rules about pillars or rooms.
Exactly. They only know that specific pillar in that specific scene based on the views they were given.
Got it. So if you point a NeRF model at a new room, even if it's theoretically seen thousands of other rooms in some data set, it treats this new one like it's the first room ever. It learns that room from scratch.
That's the core idea, which explains why it's so slow and just not ideal for dynamic real-time scenarios.
Okay. Now, moving to even more recent advancements. The paper mentions methods like DST3R, MAST3R, FAST3R, VGGT. These sound promising, directly regressing point clouds using powerful transformers, offering a more unified solution. Where do they fall short for streaming?
Right. These transformer-based methods were a big step forward, definitely more unified than the old SFMMVS pipelines, often more accurate too. But the core problem remains. They still largely focus on processing a fixed set of images.
So still batch-oriented, fundamentally.
Pretty much. While they're powerful, if you just naively ran them on a streaming input frame by frame, you'd incur significant redundant computation. They'd still have to reconstruct largely from scratch each time, without inheriting or building upon the previous results. Think about mapping that moving street again. Each new frame is treated like a whole new problem set, even if 90% of the scene hasn't changed. The transformer has to reevaluate everything. Fundamentally inefficient for continuous mapping.
Okay.
And there's another big technical hurdle with these transformers, the expensive full attention operation.
Okay, the n-squared complexity.
Exactly. Full attention scales quadratically with the sequence length, so double the video length, you quadruple the computation.
Which is just impossible for long videos.
Utterly impractical. Imagine a 10-minute video might be manageable, but extending that to an hour isn't 6 times the work, it's potentially 36 times the computation, or worse with memory constraints. It makes them completely unsuited for long videos or continuous streaming where the sequence length just keeps growing.
So even with these powerful transformers, trying to map continuously is like, I don't know, painting a masterpiece, then erasing the whole canvas and starting over for every single brushstroke. It just sounds terribly inefficient. It defeats the purpose of building a persistent map.
Precisely. It's a fundamental architectural mismatch for a true streaming scenario. You absolutely need to incrementally update and expand your understanding without constantly re-deriving everything you already know.
Okay. And what about attempts to bridge that gap before STREAM3R? Did people try to adapt these for streaming?
Yes, there were some notable attempts, but they each hit specific architectural roadblocks. For instance, SPAN3R. It tried to extend UST3R with a memory design.
Okay, adding memory sounds like the right idea.
It was. The idea was to keep some info from previous frames to avoid starting totally fresh. But the paper says it still suffers from significant accumulated drift and fails over dynamic scenes.
Drift, meaning the map slowly gets inaccurate over time.
Exactly. Imagine trying to draw a map while you yourself are constantly shifting your starting point slightly. Each small error adds up, and the map drifts further and further from reality, especially if the scene itself is changing dynamically.
Right. And the other one mentioned was CUT3R.
Yes, CUT3R. It proposes an RNN paradigm, a recurrent neural network, to handle unstructured or streaming inputs.
Okay, RNNs are naturally sequential. That seems logical.
It does seem logical for sequential data, and it correctly identified the need for incremental processing, but it ran into other classic RNN issues. Its RNN-based design does not scale well with modern network architectures.
Why not? What's the scaling issue with RNNs here?
Well, a big part is parallelism. Modern architectures, especially transformers, thrive on parallel processing across GPUs. RNNs are fundamentally sequential. You have to compute the state for time step t before you can compute it for t+1. This serial dependency makes them harder to speed up on modern hardware designed for massive parallel computation.
The hardware architecture mismatch.
Exactly. And the other big one is that RNNs struggle with long-range dependency due to limited memory size. They typically maintain a single hidden state vector that has to summarize all prior history.
The infamous bottleneck.
Right. That single state can only hold so much information. For very long sequences, information from the distant past gets diluted or forgotten. The vanishing gradient problem is related to this. It's hard to keep track of precise geometric details from many frames ago in just one fixed-size vector.
So for CUT3R, the RNN seemed like a good fit conceptually for sequential data, but as limitations in parallelization and memory capacity ultimately held it back for this complex long-range 3D task.
That's a great way to put it. What's fascinating is that both SPAN3R and CUT3R correctly saw the need for incremental processing in some kind of memory, but their specific architectural choices, whether it was memory prone to drift or the inherent scaling and memory limits of RNNs, restricted their scalability and robustness for truly dynamic, long-duration scenarios. They were on the right track, but the tools weren't quite powerful enough for the job.
Okay, that really sets the stage perfectly for STREAM3R. This next part, this is where the real ingenuity seems to come in, drawing from that unexpected domain. What if we could apply lessons from large language models to 3D reconstruction? That's what STREAM3R does, right? Tell us about this core idea, the causal transformer for online incremental 3D reconstruction.
Right. The inspiration comes directly from how LLMs handle generating text sequentially. You're probably familiar with the KV cache, the key value cache in LLMs.
Yeah, it stores the attention keys and values, so the model doesn't have to recompute them for past tokens when generating the next one. Makes generation much faster.
Exactly. It allows the model to efficiently build this growing linguistic context. Think of it like the model's short-term memory of the conversation so far. Helps it generate coherent, relevant text. The genius here is applying that exact same principle to a spatial context. The paper argues, quite convincingly, that this property is also highly desirable for addressing online 3D reconstruction from streaming data, because each step should build upon the previous reconstruction while integrating new content from the incoming frame.
Okay, but how does that KV cache concept, which is about language context, translate directly to building a persistent 3D understanding?
That's the key question. It's about maintaining a dynamic, ever-growing spatial memory, not just linguistic context. Think back to that Lego model analogy. Traditional methods make you start over. Nerf renders a perfect piece, but you still rebuild the whole model. The KV cache, in STREAM3's approach, lets the model effectively hold on to all the Lego pieces already placed in the 3D scene. It keeps the features, the keys and values representing the geometry and appearance derived from past frames readily available in this cache. When a new frame comes in, the model can attend to this cached history, integrate the new information, and update the 3D map without dismantling the existing structure or recomputing everything from scratch.
So it's like a persistent dynamic memory for the evolving 3D scene.
Exactly, which is absolutely critical for things like autonomous navigation where the world is constantly changing and you need to continuously update your internal map. It completely avoids that reconstruct from scratch problem.
Okay, that analogy really clicks. So instead of trying to process all frames at once or cramming everything into a forgetful RNN state, STREAM3R uses this LLM-style causal attention and KV cache to build a growing, persistent understanding over time. How does this translate into the actual architecture?
Well, STREAM3R reformulates point map prediction as a decoder-only transformer problem. This is a really significant architectural shift from prior 3D work.
Decoder only, like GPT models.
We're precisely like that family of models. Unlike some concurrent works using bidirectional attention or fixed-size memory buffers, STREAM3R sequentially processes the incoming frame by performing causal attention over the accumulated observations. Causal attention means it only looks at the current frame and everything that came before it. Just like an LLM generates text one token at a time, always building on the past, never peeking into the future of the sequence.
Okay, and how did they implement that in the decoder?
They went for a simplified decoder design that's quite elegant. Models like ST3R used a symmetric design with two separate decoders for pairs of images. STREAM3R gets rid of that complexity. It retains just a single decoder to process all input frames. This makes it inherently adaptable to an arbitrary number of inputs, perfect for streaming.
One decoder handles everything.
Yes, and within that single decoder, each block has two main parts. A self-atom block for frame-wise attention, which processes the features within the current frame, and then crucially, a cross-atom block for causally attending to the features of all previous observations. This cross-atom block is where the KV cache lives. It efficiently pulls relevant context from the stored history of the scene, using those cached keys and values from past frames.
Makes sense.
There's a small exception. The very first two frames follow the older DUST3R convention because there's no history yet. But after that, every subsequent frame uses this causal cross-attention with the KV cache.
That's a clever way to generalize from pairs to a continuous stream.
Yeah.
You also mentioned something called a learnable register token. Reg, what's that for?
Yes, the reg token. It's crucial for establishing and maintaining a consistent global coordinate system for the whole scene reconstruction. It gets added to the tokens of the very first frame, I1, and then essentially stays persistent in the model's memory, likely within the KV cache mechanism. This special token allows the model to learn to output the global points without introducing n separate decoders. It avoids needing complex mechanisms to handle all possible frame pairings. More importantly, it helps define the canonical world space.
Like an anchor point.
Exactly like an anchor, a fixed reference point in the model's memory. This ensures that all the subsequent incremental reconstructions from new frames get consistently registered or aligned to this single, stable global coordinate system defined by that first frame and the reg token.
Without that, I guess the global map would drift really badly as the camera moves.
It would be incredibly difficult to maintain global coherence over a long stream otherwise. You'd likely see severe accumulating errors or drift. This token provides that essential grounding. You can almost picture the flow, input images, stream in. The VIT encoder extracts features from the current frame. The decoder's causal attention integrates these new features with the stored features from past frames, the KV cache, and that reg token keeps the whole evolving 3D map anchored to a stable global origin. Result, incremental 3D reconstruction without significant drift.
So it's dynamically mapping the scene and understanding its own movement within that scene simultaneously. That sounds incredibly powerful for real-world robotics or AR. What specific 3D attributes does it actually predict per frame?
It predicts a really comprehensive set for each frame, giving it this rich, multifaceted understanding. First, there's the local point map, xlocal.
Local meaning from the camera's viewpoint.
Exactly. It's defined in the coordinate frame of the viewing camera. Think of it as the immediate egocentric view what the camera sees right here, right now. Second, and just as important, is the global point map. Global, this one is in the coordinate frame of the first image I1, providing that consistent global scene representation we talked about, anchored by the reg token.
So it builds one big coherent map over time.
Precisely. It continuously expands this global map with new observations as the camera moves, even through a really large space. Then, along with both point maps, it provides confidence maps, local to global. These give a measure of prediction reliability for each point.
How sure is it about that specific 3D point?
Exactly. And this isn't just a nice-to-have, it's incredibly valuable for downstream tasks. Think about a robot navigating it can use these confidence maps to maybe avoid areas where its perception is uncertain or plan paths through regions it understands well. It leads to much more robust, safer systems.
That makes sense. Knowing what you don't know is important.
Absolutely. And finally, it estimates the relative camera pose. This includes both intrinsics and extrinsics.
Intrinsics like focal length, extrinsics like position and orientation.
Correct. Intrinsics describe how the camera sees the world, its internal properties. Extrinsics describe where the camera is in 3D space and its orientation relative to that global scene. So, STREAM3R is simultaneously building the 3D map and tracking its own movement within that map.
Wow.
And apparently, this redundant prediction, predicting local maps, global maps, confidence pose, actually helps simplify the training process. It also makes it easier to train on data sets that might only have partial annotations, like maybe only single-view depth data for some scenes. The model still learns effectively because it's trying to predict multiple consistent views of the world.
Very smart, building multiple linked representations. And beyond the architecture, how does this LLM inspiration carry over to the actual training infrastructure? Are they just borrowing ideas or using actual LM tools?
Oh, they're absolutely leveraging actual state-of-the-art LLM-style training tools and infrastructure. The paper really stresses the inherent compatibility of STREAM3R's design with modern LLM-style training and inference techniques.
And that's a big advantage.
It's a huge advantage.
Okay.
It means STREAM3R gets to immediately benefit from years of intense optimization work done for large language models. They don't have to reinvent the wheel for efficient training and inference. We're talking specific techniques like window attention for managing very long contexts efficiently, the KV cache itself, not just as a concept, but as an optimized software primitive for fast inference, things like bfloat16 mixed precision training, which saves memory and speeds up computation, and maybe most crucially, flash attention.
Flash attention, yeah, that made waves in the LM space. How does it help here?
It's a game changer because, like we said, standard attention scales quadratically with sequence length. In streaming 3D, that sequence can get incredibly long. Flash attention dramatically reduces both the computation and the memory footprint of the attention mechanism. It makes attending to very long histories computationally feasible on current hardware. Without it, processing long streams with global context would likely just hit a wall.
Okay, so it's essential for making the long context work efficiently.
Absolutely. And they also mention gradient checkpointing. This is another technique common in large model training. It lets you trade extra computation during training for significantly reduced memory usage. You recompute some intermediate values instead of storing them all. This allows training much larger, deeper models than would otherwise fit onto the GPUs.
So these aren't just minor tweaks, they're enabling technologies.
Exactly. They're what allow the ambition of STREAM3R, this continuous long context 3D reconstruction, to become a computational reality. It's about inheriting this highly optimized computational backbone from the LLM world.
That's a powerful synergy, bringing battle-tested HPC techniques from one domain to supercharge another. Okay, let's talk training. What are the key objectives and what kind of data does it need to learn this complex geometric understanding?
Right. The training relies on two main objectives. First is the confidence-aware regression loss, LPUNF. It's described as a generalized form of the point map loss from DST3R. It basically penalizes the model based on two things: how confident it is about a 3D point prediction, and how far off that prediction is from the ground truth position, using square difference. Importantly, it includes scale and variant supervision.
Scale invariant, meaning it can work even if it doesn't know the true physical size of things.
Yes, exactly. It can learn accurate relative depth, even from images where the absolute scale isn't known, which is common in real-world data. But it also supports metric scale prediction when that ground truth is available, so it's flexible. The second objective is the camera prediction loss, LPOS. This focuses on making sure the model accurately estimates the camera's position, orientation, and its internal properties, intrinsics. It parameterizes the pose using a quaternion for rotation, which is generally more stable than Euler angles, a translation vector for position, and the focal length. The loss just minimizes the square difference, the L2 norm, between the predicted and ground truth camera parameters.
Okay, so learn the scene structure and learn where the camera is simultaneously.
That's the goal. The two objectives work together.
And to learn these general geometric priors, it must need a massive amount of diverse data, right? What does a training data set look like? Why is diversity so critical here?
You're spot on. Data diversity is absolutely paramount for generalization. The model is trained end-to-end on a large and diverse collection of 3D datasets. The paper mentions using 29 datasets in total, with 15 main ones sampled more heavily during training.
29, wow. Any familiar names in there?
Oh, yeah. Lots of well-known benchmarks covering different domains. You've got things like Co3DV2, Scanet plus Co, Scanet, HyperSim, Dynamic Replica. These often cover static and dynamic indoor scenes, objects, both realistic and synthetic data. Then there's Tartanair, MapFree, Megadepth, ARKit scenes, Wild RGBD, Waymo, Bedlam. These push into outdoor scenes, large-scale mapping, autonomous driving data scenes with lots of human motion.
So a real mix of indoor, outdoor, static, dynamic, real, synthetic.
Exactly. The breadth is critical. By learning from such a wide variety, static and dynamic scene and objects, indoor and outdoor, realistic and synthetic data, STREAM3R develops these robust geometric priors. It's not just memorizing specific scenes, it's learning the underlying principles of 3D geometry, how objects typically behave, how cameras move across all these varied contexts. This allows it to generalize to new, unseen scenarios, which, as we discussed, was a huge hurdle.
Right, unlike NERF, which starts fresh every time, this learns general rules.
Precisely. If you only trained it on static indoor scenes, it would be lost trying to map a dynamic outdoor street scene. This extensive data diet allows STREAM3R to build a more fundamental understanding of our 3D world.
That's a serious training regimen. What about the nitty-gritty implementation? What models are used? How long does it take?
Architecture-wise, it builds on strong foundations. It uses CrocoVIT pre-trained weights for the vision transformer encoder, so it leverages knowledge learned from massive image datasets already. Then it retrofits a decoder and uses DKT heads for the actual point map prediction. It's standing on the shoulders of giants, so to speak.
Okay. And the training computation?
It's significant. The paper states it's trained on 8 NVIDIA A100 GPUs over 7 days.
A full week on 8 A100s. Okay, that's serious compute.
Definitely. It performs 400K iterations with a batch size of 64. And interestingly, each batch randomly samples 410 frames from a random training scene. This variable sequence length per batch probably helps generalization too.
And input image sizes.
They also vary that. Input frames are cropped into diverse resolutions, ranging from 224 by 224 to 512 by 384. Again, helping the model be robust to different input scales and aspect ratios you'd see in the wild. And for efficiency and stability during that intense week-long training, they use those advanced techniques we mentioned. QK norm in the transformer layers for stability, flash attention for bfloat16 mixed precision training for speed and memory, and gradient checkpointing to optimize memory usage to fit the large model. These are essential for making it feasible.
Okay, that sounds like a massive computational effort backed by cutting-edge techniques. So the big question, what does all this technical horsepower actually achieve? Let's look at the results, starting with depth estimation. How well does it do?
The results for depth estimation are really quite strong, showing both accuracy and efficiency gains. Let's start with single-frame depth predicting depth from just one image. Here, STREAM3R achieves state-of-the-art compared to streaming-based methods. But what's perhaps more impressive is it even performs best compared to VGGT on Scintol, KD, and NYU2.
VGGT is a strong baseline, right? And those are diverse datasets.
Exactly. Scintol, KD, NYU2 cover dynamic scenes, outdoor driving, indoor scenes, synthetic, and real data. Performing best there indicates really strong zero-shot generalization. It suggests the model has learned robust geometric priors from that diverse training data.
And the metrics they use, standard ones.
Yes, standard metrics. Absolute relative error, ABSREL, the average relative difference from true depth, and 1.25, which is the percentage of predicted depth points that are very close within a 1.25 factor of the true depth.
Okay. What about video depth? That seems more aligned with STREAM3R streaming design.
That's where it really shines, as you'd expect. When evaluating on video sequences, both using per-sequence scale and true metric scale, it surpasses optimization-based baselines like variants of DUS3R and MAS3R, even MONS3R GA, which handled dynamic scenes. And critically, compared against the previous streaming state-of-the-art, which was City3R.
The RNN-based one.
Right. STREAM3 achieves higher accuracy on all three benchmarks, Scintol, Bon, Kitty, while also running 40% faster.
40% faster and more accurate. That's significant.
It's a huge gain, nearly twice the frames per second processing capability. That's massive for real-time applications where latency matters.
That speed up really shows the benefit of the LLM-inspired architecture and optimizations.
Absolutely, and it gets even better. They have a specific variant called STREAM3R W5. The W5 means it uses sliding window attention for constant cache. only looking back at the 5 most recent frames.
Sacrificing some long-range context for speed.
You'd think so, but interestingly, this variant exceeds STREAM3R, the full cache version, on Bon and Kitty despite accessing only 5 past frames, and it achieves the fastest FPS among all streaming-based methods.
Faster than C3R too.
Much faster. It hits 32.93 FPS on Kitty, whereas C3R was at 16.58 FPS, so basically double the speed of the previous state-of-the-art while maintaining or even improving accuracy on some benchmarks.
Wow. That really demonstrates efficient real-time capability.
It really does. This combination of superior accuracy and significantly faster inference speed, especially with the windowed version, is frankly a game changer. For real-time robotics, drone navigation, AR, where every millisecond counts for decisions or user experience, processing faster without losing quality is paramount. Systems can react quicker, more reliably.
So it's fast and accurate on depth. What about full 3D reconstruction, building the whole point cloud? How does it compare there?
Again, strong performance for full 3D reconstruction. They tested it on challenging datasets like 7 scenes and NRGBD. It achieves better performance compared to optimization-based methods and strong baselines, including SPAN3R, FAST3R, CUT3R, and SLAM3R.
Using what metrics for reconstruction quality?
Standard ones here too. Accuracy, ASA, how close points are to ground truth. Completion, how much of the scene is captured, and normal consistency, ANC, assessing surface smoothness and orientation, and the speed advantage. Also significant, it's over 50% times faster during the inference compared to CT3R on this task as well. Another big leap for practical use.
Is it the absolute fast?
Not quite. They note that SLAM3R is even faster, but it yields noticeably lower reconstruction accuracy than our method. Part of the reason might be SLAM3R using a lower input resolution. 224 by 224. So STREAM3R strikes a really good balance, high quality and impressive speed without compromising on input detail as much.
That efficiency of the causal transformer design really seems key. Did they test a version without causal attention just to isolate its effect versus the overall architecture?
Yes, good question. They did test a variant called STREAM3R, where FA stands for full attention. This version replaces causal attention with standard full attention during training, though it wouldn't be practical for live streaming inference. And interestingly, STREAM3R yields comparable performance compared to VGGT and even better results on the completion metric.
So the core architecture is strong even without the causal constraint.
Exactly. It highlights the effectiveness and generality of their underlying method. It suggests that while causal attention is crucial for the streaming efficiency and real-time inference, the core transformer design, the huge data set, the loss functions, these are fundamentally robust for high-quality 3D reconstruction anyway. It helps disentangle which parts contribute to what benefits.
That's a really valuable insight. Okay, final performance area. Camera pose estimation. Tracking the camera's movement. How does it do, especially in those tricky dynamic environments?
This is another area where it really excels, which is vital, as we said, for robotics and AR. They tested it on tough datasets: Cintel, 2M Dynamics, and Scanit. These are known to feature substantial dynamic motion that often trips up traditional SFM and SLAM pipelines.
Right, moving objects or people really mess with those older methods.
They really do. A key capability here is that STREAM3R operates without requiring camera calibration. You don't need to pre-calibrate the camera. It learns the intrinsics from the data. That's a big plus for real-world deployment.
Okay, and the results?
It establishes the strongest performance among streaming approaches on these challenging dynamic data sets. It notably surpasses CUT3R on both 2M Dynamics and Scanit, showing it's particularly robust in these dynamic environments.
Better than the dedicated streaming methods?
Yes. While some optimization-based methods, which run offline and take longer, might still achieve slightly lower absolute error values overall, STREAM3R provides the best combination of speed and accuracy for online real-time processing of dynamic scenes among the streaming contenders. And that ability to accurately track pose online without calibration in dynamic scenes, that's incredibly crucial. For a robot navigating, for AR overlays needing precise alignment with a moving real world, it's essential. Excelling where traditional SLAM often struggles is a major technical leap.
The performance numbers are definitely compelling across depth, reconstruction, and pose estimation. Now let's dig into the why. The ablation studies. How do they directly show their decoder-only transformer and causal attention are truly better than the RNet approach in CUT3R?
They set up a very direct comparison. The goal was to demonstrate the effectiveness of decoder-only transformer against RNN design in the sequential 3D point map prediction. And crucially, to ensure a fair fight, Both STREAM3 and CUT3R were retrained using the same dataset and pre-trained model weights initialization and used the same hyperparameters and compute resources.
So a real apples-to-apples comparison of just the architecture.
Exactly, isolating the architectural merits. And the results showed clear advantages for STREAM3R. First off, significantly faster training and convergence. STREAM3R converges faster compared to CUT3R. And get this, it performs 60% more training steps within the given time.
60% more steps, even though it's attending to a longer context, which sounds like more work.
It does sound counterintuitive, doesn't it? But the technical explanation boils down to how they handle information flow and parallelism. The UT3R architecture requires a state update operation after each state readout interaction. This is inherently sequential, step by step, which bottlenecks parallel processing on GPUs. In contrast, STREAM3 directly attends to cached features of existing observations. This, combined with modern optimizations like flash attention, leverages the parallelism of transformers much better. So even though it looks at more past data, the overall computation is structured more efficiently for modern hardware, leading to faster training iteration.
That's a huge insight. It's not just raw speed, but the learning speed and the quality of the global map benefit. Did this advantage show up more in the global map reconstruction?
Absolutely. That's where the difference was particularly stark. They observed improved global branch convergence. While the convergence of head local, the local frame understanding, was pretty similar between the two architectures.
They both figured out the immediate view, okay.
Right. But for head global, the global branch responsible for building the consistent overall map, STREAM3R's architecture showed noticeably faster convergence speed and reaches a better final performance.
Okay, why would the global understanding benefit more from the transformer KV cache than the RNN?
It really points to that limited memory capacity of the RNN's single hidden state. It seems that single state just struggles to accurately register incoming frames into a consistent global coordinate system over long sequences. It can't easily retain and access all the necessary fine-grained historical geometric detail needed to prevent drift in a large map. The KB cache, however, offers a richer, more directly accessible history. It's not just a compressed summary. It's a detailed, queryable record of past observations features. This direct, efficient access allows the model to build and maintain that globally consistent 3D map much more effectively over time, reducing drift and improving accuracy, especially important for large-scale mapping or long-term robotics.
So it's about the quality and accessibility of the memory, not just having some memory. That's a critical distinction. And the final quantitative results from these ablation models confirm this.
Yes. When they evaluated the models trained for the same number of iterations, STREAM3R's architecture consistently achieved better performance on both tasks, video depth estimation and 3D reconstruction, compared to the retrained CU3R. It's strong empirical evidence backing their architectural choices. The causal transformer with its KV cache really is more effective for this sequential 3D task.
Okay, the research is clearly pushing boundaries, the results are impressive, but no model is perfect. What limitations do the authors acknowledge for STREAM3R, and what do they see as the next exciting steps?
Right, even groundbreaking work points to future improvements. One key limitation they mention is that the naive causal modeling naturally suffers from error accumulation and drifting.
Even with the KV cache?
It performs much better than prior methods, but the fundamental challenge of incremental systems remains. Small errors can still compound over very, very long sequences. They suggest that some inference strategies can be proposed to alleviate this issue in future work.
Like what? Loop closure.
Exactly. Things inspired by traditional SLAM, like detecting when you've returned to a previously mapped area, loop closure, to correct accumulated drift. Or maybe incorporating some form of lightweight global optimization periodically without losing the online nature. Second, they note that STREAM3 is currently still a regression model with deterministic outputs. It predicts the single most likely 3D structure and pose.
It doesn't give you probabilities or alternatives?
Not inherently. It doesn't model uncertainty in its output or generate multiple plausible interpretations, which could be useful in ambiguous situations. So, extending it further into an autoregressive generative model is highlighted as an exciting future direction.
Generative, like it could create variations or predict.
Precisely. That shall further unlock a series of downstream applications. Imagine not just reconstructing what is there, but maybe sampling from a distribution of possible 3D scenes if the input is ambiguous. Or even predicting how a dynamic scene might evolve. Where might that car turn next, based on learned dynamics?
So, already impressive, but they're eyeing the next frontier. Not just reconstruction, but generation and prediction in 3D based on observations. That's truly mind-bending. Are there more LLM training tricks they might borrow?
Yes, they suggest integrating more training techniques like MLA multilayer aggregation to further boost the training efficiency and performance. MLA could allow the model to aggregate features across different transformer layers, potentially creating even richer representations.
So the cross-pollination isn't over yet.
Far from it, it seems. It shows this convergence between LLM advancements and 3D perception is likely to continue, yielding even greater efficiencies and capabilities. This work really bridges geometric learning with scalable sequence modeling beautifully. It paves the way towards more general-purpose, real-time 3D understanding. But it also makes us think about the next set of technical challenges, right? Beyond what the paper details. How will these systems handle extreme lighting changes, bright sun to deep shadow, fog, rain? How robust will they be to totally novel objects or environments way outside the training data? How can they adapt quickly to dynamic changes in the environment itself, like furniture moving or construction?
And the computational needs for real-time decision-making.
Exactly. What are the precise computational budgets for integrating this into complex autonomous agents that need instantaneous safety-critical decisions, not just mapping, but complex planning and interaction? And how do we ensure long-term map consistency in highly unstructured, constantly changing worlds where drift is always a potential issue? These are the deeper questions this kind of research helps us tackle. It gives us a powerful new tool.
Indeed. The potential for STREAM3R as a foundational piece in future AI is huge. You could see it powering next-gen robotic perception, letting robots build accurate maps with unprecedented speed, even in dynamic factories or disaster zones.
Absolutely.
Or revolutionizing AR, making overlays perfectly aligned in real time, blurring the lines between virtual and real, and even creating truly dynamic digital twins, constantly updated 3D models of factories or cities for simulation, monitoring, remote operation. It feels like a significant step towards machines that really perceive and interact with our evolving world with a new level of understanding. What a deep dive. We've really unpacked how STREAM3R uses causal transformers inspired by LLMs to revolutionize real-time 3D reconstruction from streaming images. We saw how it tackles those critical issues: scalability, drift, efficiency, outperforming state-of-the-art methods across depth estimation, 3D reconstruction, and camera pose cracking, especially in dynamic scenes.
So the results are certainly impressive on those fronts.
This technology feels like more than just an incremental step. It seems like a paradigm shift in how we approach 3D perception for dynamic environments, making fast, accurate, continuous 3D understanding more accessible, more robust than before.
It definitely pushes the boundaries of what's possible in real time.
So what does this mean for you, the listener? Imagine a future where almost any camera, maybe on your phone, a drone, a robot, a car, can instantly map its surroundings in full 3D. Not just static rooms, but dynamic scenes, moving objects, people all processed in real time. What new applications might this unlock that we haven't even thought of yet? Maybe a new era of truly adaptive robots. AR experience is so seamless they're indistinguishable from reality.
The possibilities are vast when machines can truly see and understand the dynamic 3D world in real time.
It really feels like a foundational step towards machines that truly understand the ever-changing world around them.